Welcome back to ECE 442-542. We're getting close to the end of the semester if I'm announcing teacher course evaluations and final exam. Final exam is on the last day of finals, and it's at 1 to 3 o'clock in this room. Teacher course evaluations, you've probably received the email, but I don't know that too many have responded. I think the percentage was 7% had completed that, which is fine. This is still a week or two away from that deadline of May 2nd. Homework 7 is due on a Saturday this time, so that it's not due during the last week, just before your senior design day, I guess. And if you're doing the project in 542, that's due on the 2nd. That's the last day of class. I just this afternoon decided to put together some material. Well, I didn't just decide, but I did it this afternoon right before class. There's a couple of more examples, and there's notes and videos for those. It's relative to rule number 5 on the root locus. How do you calculate the angle of arrival and angle of departure? And hopefully those will make some sense. But you'll start to interpret or understand which of these diagrams might go for the same particular set of poles and zeros. This is for angle of arrival. How do the branches of your root locus arrive at the complex zeros? In what direction? And that's indicated by alpha sub A in both of these. And both of these particular options have the same geometric structure on the poles and zeros, but depending on the particular values on those pole and zeros, you might have what you see on the left or you might have what you see on the right. And I try to go through that or talk about that in some of that additional material. There's A and B for lecture 7.1. It follows up on the last lecture that we talked about, which was lecture 7.1, dealing with rules 4 and 5. And A is actually, maybe I should have labeled them differently, but A is for departure angles and B is for the arrival angles. Today what I want to do is talk about PID control, where it comes from or how to connect with that and what it really means in terms of poles and zeros in the z-plane. When you see PID controller, hopefully now you immediately think about where some of those poles and zeros might be located. And the final is comprehensive. The question was, the final covers everything, and my answer is the final is comprehensive. So yes, you now have, but really the material has been cumulative, so I could give you, I always joke about this, but it's not really a joke. I could give you one problem that talks about the material at the very end of the semester, and it really sort of relies on all of the material preceding that in the course. So it's really, whether it's comprehensive or not, it's sort of built in to be comprehensive, so I'm going ahead and letting it be comprehensive. But today we'll probably see the first bullet, which is the PID control. I'll scroll through the structure and what that looks like in the analog case and the discrete time case, and we'll derive that so that you'll see that we indeed, when we say PID control for the digital case, we have two poles that are automatically fixed in the z-plane, and we get to sprinkle in the z-plane two complex zeros or two real zeros. We have the choice of locating two zeros in the complex z-plane. With that, that leads us into what I call or consider a generic controller design, where now we do have this flexibility of shaking poles onto the z-plane wherever we want, shaking zeros wherever we want. But now that we have this insight into the root locus and how the PI and the PID controllers work, we might be better informed as to how to sprinkle those poles and zeros in the z-plane generically. And we will eventually get into the state space control design, and that will be dealing with, well, we'll do that on homework number 8, and that will be sort of an extra credit assignment. It won't cost you if you don't do it. It will help you, but it will also be required for the final, the material. So you might as well do it, but whether you want to do it for points is up to you. PID control is fitting into the structure that we've had all along. Here you can see that maybe, or notice that I haven't explicitly put any arguments on the signals. There's not an S or a Z. This can be applied in the analog case or the discrete time case. And what we will do is first show what it looks like in the analog case, and then we'll move into the discrete time case. Here it, I think, seems fairly intuitive to talk about a PID controller in the frequency domain for the analog system. You have your proportional term, you have your integral term, which is now division by S in the Laplace setting, and you have your derivative term, which is multiplication by S. Each of those, now you essentially, this is taking the error signal, that's the signal coming out of the first summing junction that's comparing the reference input with the output. You take the error signal and you scale it proportionally, or you scale the integral of that error signal, or you scale the derivative of that error signal. And all of those adjustments provide you with flexibility in how you're going to control and manipulate the behavior of your closed loop system. The addition of those, you could really sort of think of that as having 3 parallel signals going in to form your input U into the plant, because you're adding up the proportional piece, the integral piece, and the derivative piece. This should be somewhat intuitive in terms of the structure. If somebody says PID control, you could actually just immediately write down the P, the I, and the D pieces of that PID controller. It doesn't look quite as clean in discrete time, but the PID and the analog time is fairly clean. You can now perform some algebra on that expression. You can factor out the gain from all 3 terms, and you now have the gain factored out, and the integral term has as its gain k sub I over k sub p, and the gain on the derivative term is now k sub d over k sub p. Or you've now normalized this, you've sort of put it into a time constant. Well, not really, so I won't say that. But now you've put it into a form that allows you to adjust that gain after you've maybe established the integral gain and the derivative gain. You can now adjust the gain outside, like in our typical block diagram for the root locus. You can move those coefficients on the last 2 terms around and consolidate them into t's, and hopefully it's clear that these t's are actually times. What are the units on S? Or what does S represent? It's a frequency, isn't it? That's in our frequency, and typically it might have units of radians per second. And radians you can sort of just think of as almost dimensionless. And so now you have t times per second. And you need this term to be compatible with something that's dimensionless. So now you have t times s, or t is in seconds. This t sub I could be referred to as the integral time. T sub d could be referred to as the derivative time. And those are now units of seconds. And here's the notation then that is associated with that last representation of a PI controller. Meaning if you bought a PID controller from a company, it might come with a proportional gain, it might come with a knob that says integral time, and it might come with a knob that says derivative time. Now you're adjusting those knobs to achieve the behavior that you want from that controller. The reason why I'm showing these different representations of the PID controller is so that if somebody now hands you an analog controlled system that's a PID controlled system, and they say, put this into a digital system, you'll be able to essentially, or very quickly, just use their same gains that they had in the analog case, except now you need to introduce a sample period. And boom, you have the digital controller. But that will now fall into place after we derive this representation. But here's the digital form of the above expression. And that last, or the second row, is actually all scaled by k. That's what I'm meaning by that looped arrow in blue. But in this particular case, what do you see, or what might you start thinking about when you're looking at that particular expression? What's really going on in this PID controller? U is the input to the plant, and now you've sampled that, and you've also sampled the air signal. How many sort of memory locations, or how much do you have to store the air signal in memory? You have the current air, which is E of n. That's the air at the present time. You have the air one sample period prior to now, and you have the air two samples ago, which means that you now scale the existing or the present air signal, E of n, and then you add to that algebraically a scaled version of the air one sample period before, and you add to that a scaled version of the air the previous time. So you have two delays in your air signal that you're adjusting to push into the input to the system. There's also memory in here because of that U of n minus 1. That U of n minus 1 says that's the previous input that you applied to the system. You're now just modifying that with the present air and the air two sample periods before. That's really what this is saying. It's saying adjust the previous input that you applied to the system with some of the airs and weighted, those weighted airs. That's what the PID controller is really doing. What I would like to do is sort of quickly go through how we get from C of S to C of Z. And remember, C of S in the very basic sense is just Pi and D, just the algebraic sum of the proportional, the integral, and the derivative term. And how do we go from there to this equation? That's what I want to basically just show very quickly. You can go through some of the intermediate steps if you're having trouble sleeping tonight or some other night. So don't worry too much. Just try to follow along the derivation. Here is the analog version of the PID controller written in terms of the proportional gain, the integral time, and the derivative time. The second step in the derivation is simply to factor out this 1 over s term from all three terms in the bracketed expression. And that says then that you have an s squared, you have an s term, and then you have a constant term inside the parentheses. But once we have that s sitting outside by itself, we can now cross multiply both sides. We push the e, the Laplace transform of the air signal, to the right-hand side of the equality sign, and we multiply both sides by s, and this now gives us a frequency domain representation of the PID controller. Question? So now the question, I think, was, could we start, well, so yes, we could z-transform this equation. What I'm wanting to do is show where this time domain equation comes from when we start with an analog controller. That's what I'm trying to show now. And really, I didn't show you how you get this discrete time controller. I just said, here it is. Now we're trying to derive it. Meaning, if we have the final exam right now, you should be able to take this last row that you see into the time domain. This should be on the 320 exam, final, right? You should be able to do this based on your knowledge of ECE 320, which is just Laplace transform. Inverse Laplace transform that system of equations. And what does that represent? That just represents the connection of the air to the input. What happens in the time domain when we have on the left-hand side s times u of s? What's that look like in the time domain? That's just a derivative, isn't it? And then we have, on the right-hand side, we have a derivative of the air. We just scale the air for the middle term, and then we differentiate twice the air. And I don't know what happened to the top of my time, but somewhere it disappeared. So we have a time warp here, but maybe it will reappear after I scroll or don't scroll. That blue time domain expression you should have been able to intuitively see from the black equation in the middle of the screen. Now what we want to do is go into the frequency domain using a discrete equivalent, and in this case, let's use the backward Euler because that actually preserves stability in that discrete equivalent process, which means that if we wanted to start in the S domain, then we could replace that S with one of these two versions of Z on the right. But the furthest one on the right is really sort of what we are going to do in the time domain. If you look at what this would do in the time domain on the far right, view that as an operator on a signal. If you applied 1 minus c to the minus 1 divided by t to, let's say, an e of z, what would that look like in the time domain? So we're reviewing for the final exam. You're scaling both. You have two terms, don't you? And they're just going to be compared with that subtraction sign. They're both scaled by 1 over t. So whatever the sample period is, you would divide by that. And then you simply take e of z into the time domain. That's the 1, scaled by 1 over t. And what's this z to the minus 1 as an operator? That's just a unit delay. So now you subtract e of n, you take e of n and subtract from that e of n minus 1 and divide both by t. And that's basically equivalent to this in the time domain, this s, and what's multiplication by s in the time domain? Derivative. So does that make sense? We're now going back to the very beginning of your calculus class and saying, how do you approximate a derivative? Oh, you take the current value minus a small variation in that value and divide by the time separation between those. That's all that we're really doing with the backward Euler. And we have a couple of different times that we have to do that in this blue equation. We have a derivative of u, we have a derivative of e, and then we have a second derivative of e. So we'll have to sort of repeat that twice. But hopefully this row now makes sense from the time domain blue equation in the upper half of the page. U prime is just u of n minus u of n minus 1 over t. When you see an e prime, that's an e of n minus 1 over t. The 1 over t sub I e becomes 1 over t sub I e of n. Just a scaled version of the present value of the air signal. And then, when we have the second derivative, then we have to go through a little bit more gymnastics. Now we're taking the difference between the first derivative pieces. And this red curly brace underneath is now going to say, okay, do that one more time with e prime of n, do it one more time with e prime of n minus 1. And you can predict what that's going to look like. This is just what we need to insert in that red curly brace. It all has to be divided by capital T, but now we simply replace e prime of n with its approximation, and we replace e prime of n minus 1 with its approximation. And if we plugged all of this in the curly red brackets in for the last blue bracketed, we would have our complete time domain expression for a PID controller. And that's what I'm doing here. For whatever reason, I decided to change the argument on my time index. Now it's L. I got tired of using little n's, but this is just a time index L. And here is that previous time domain version of our PID controller written in terms of air signals. We have 3 of those airs: the present air, the air 1 time step before, and the air 2 time steps before, and a memory of the previous input to our plant or into our system. And now, instead of getting all bogged down with these big coefficients, I'm just going to collapse them all to an alpha 0, an alpha 1, and an alpha 2, and kind of keep track of it that way. Another final exam review question: can you take this equation into the frequency domain in terms of alphas? That should be a straightforward process. It's just involving some delays. It's simply scaled delays, and you know how to z-transform delayed equations. E to the n minus 1 z-transforms into z to the minus 1 capital E of z. So you have to be able to hit the shift key to get into the frequency domain. This is what you would end up with. You have a z to the minus 2 scaled by alpha 2. You have a z to the minus 1 scaled by alpha 1. And you have an alpha 0 with just the z transform of E. And the first term on the right of that equal sign, little u of one time step ago, becomes z to the minus 1 capital U of z. Again, this is reviewing for the final. Let's now manipulate that a little bit. We can factor out the common z transform of E on the right. We can move the u terms to the left. We're just doing algebra. And now we have our u term on the left and our e terms on the right. And this is begging to be taking a ratio to give us u over e, which is our transfer function of our PID controller. But it should be clear how we just arrived at this last row that's on the screen now. And there's our transfer function of our controller. It's a linear combination of z to the minus 1 scaled by these alphas, and we have a 1 minus z to the minus 1 downstairs. No coefficients downstairs, just a 1 minus z to the minus 1. But I want to write this in terms of, so this red shouldn't really be there in the first sort of step in this derivation. Now I want to convert that into positive powers of z instead of delayed versions or z to the minus 1s. I'm going to now multiply numerator and denominator by z squared and clear the z to the minus 1 terms. And now I have everything written in terms of z's. And downstairs, what do I have? Z squared minus z, which I can factor into a z and a z minus 1. And there where my poles from my PID controller are fixed. I have no more manipulation on the poles. If I say PID controller for a discrete time system, you immediately can put a pole where? At the origin, and another pole at 1. What's the pole at 1 do for you? Do you remember? So I've heard stabilize and I've heard zero error. So we actually have to trade off those two, don't we? We need steady state accuracy when we put a pole at z equal to 1. That's what we're focusing on, is steady state accuracy. That is then going to be traded off by transient performance. And we will achieve the transient performance adjustment in the numerator by selecting those coefficients. Here, let's adjust that just ever so slightly by factoring out or making the numerator with all the gains factored out such that without the gain we have a monic polynomial upstairs, or the leading coefficient, if we don't consider the gain, is just 1. So we have z minus beta 1, z minus beta 2. That's a second order polynomial. And downstairs we have z times z minus 1. When I say PID for the z domain, this you can write down. And boom, work with that. You don't have to rederive anything. You can just immediately write down this structure for a PID controller. Now, if I wanted you to implement it, with a microprocessor, then you would need to take this into the time domain and worry about delays and scaling your error signals and the input. But this is now what you want to be playing with when somebody says, oh, you have a PID controller. This is the structure that you can generically think of. What does that represent? Here's the picture that you might be seeing as you're dreaming about PID controllers. If somebody gave you that transfer function, maybe you're actually envisioning this pole zero diagram. You have two poles and they are fixed. One is at z equal to 0, that's at the origin in the z-plane. What's the speed of that? It's fast, isn't it? It's really fast. And that's really there so that this transfer function is causal in the PID controller. The pole at 1, you told me, helps you improve steady state accuracy. And that's the I part of your PID controller. That's the integral part. That's giving you that pole at z equal to 1. These other circles, now you can move those at will to however you want to locate those in the z-plane to achieve the closed loop behavior that you want. That's the idea behind this PID controller. Boom, you force a pole at the origin and a pole at 1, and you have the flexibility to move around two zeros. They don't have to be on the real line, they could actually be complex. Once you've picked those, now you can simply adjust the knob K using your root locus design approach. And what we will talk about in a little bit, hopefully, is, oh, wait a minute, I want my desired poles to be at certain locations in the z-plane. Well, maybe we can use the phase angle condition to determine what these betas need to be or where those zeros need to be in order to accomplish our closed loop poles where we want them. That's upcoming in the next example or in an example. But is it clear what you have if somebody says PID controller? You now have this structure either in the z-plane or in the transfer function. You have two fixed poles and two zeros that you can adjust. And I want to say that one more time. Now we're saying it verbally or in writing. If you are designing with a PID controller, you've placed a pole at z equal 1, and you've placed a pole at the origin. You then have two more parameters to play with, actually 3. You have the zero locations and the gain. You can adjust now or select 2 zero locations and then adjust the gain. That's what you have available to you with a PID controller. Let's now use that to look at a particular example. So suppose somebody gives you a g of z of 1 over z minus 3/4. That's about as basic of a problem as you can have given to you. What do you do now if somebody says, oh, here's a system and we want to control it? And they've given you a z-plane. So they're hinting to maybe do something relative to the z-plane. How could you now help them if they've now laid a z-plane in front of you and they say, oh, can you come play with me? I have g of z equal to 1 over z minus 3/4. What are they wanting you to do? If you were playing checkers or tic-tac-toe, you would put an X somewhere, wouldn't you? If they drew this tic-tac-toe board, that's really what we're suggesting you do now. Can you put down the poles and the zeros on the z-plane for your given plant? And that shouldn't be hard, right? Now we have a pole right there at 0.75. If somebody said, okay, control this system, put it in a closed loop configuration, what would you see if somebody said, control this with a proportional controller in a closed loop setting? What would you now be able to do to this diagram if somebody said, control this with a proportional controller, a P, in the PID controller? You just want a gain. If you now have a gain in a closed loop system, what does that beg you to do with this z-plane plot? Root locus. Now all you have to do is sketch the root locus for this pole zero diagram, and that would give you all of the potential closed loop poles as you adjusted the gain from 0 to infinity. And what would that root locus look like? How elaborate is that root locus? Is that what it looks like? Does that satisfy the phase angle condition? Could, if I now said on the final, so maybe that's not it, but if I said, is this point on the root locus? How would you argue that that is or is not on the root locus? So we have one pole and something about 180 degrees. What is that something? We know that the closed loop system has what structure if it's proportional control? This you probably should have sort of memorized, right? It's CG over 1 plus CG, and C, our controller, is just a K. So this is now KG over 1 plus KG. And what determines the dynamic behavior? The denominator, right? The numerator of our denominator. You can really get yourself chasing your tail if you want to talk about numerators and denominators, but it's the denominator of T of Z that you're interested in, and it ends up being the numerator of that denominator, right? But what are we doing? Well, we're looking at the poles, or I'm sorry, the values of Z that cause that to be true. And that, if you solve it for Kg, is equal to -1. And -1 in polar form is just 1 at an angle of -180. And if K is non-negative, if K is positive, we know the angle of G has to be -180. Which says then that the angle due to all of these poles and zeros algebraically needs to sum to 180. And you would go up here and you would say, oh, let me find all of the angles associated with these poles and zeros. You don't have very many poles and zeros. That's supposed to be a straight line, and you would measure the angle from that pole to that red dot. And you would say, okay, I have all my zero angles added up. I don't have any of those, so that's nothing, minus all of my pole angles. And there's my pole angle, theta sub p. And I want that to equal -180 if that point is on the root locus. Is that angle theta sub p 180? No. So that point is not on the root locus. Okay, do you move on to the next question on the final exam, right? You've answered this. Is that red dot on the root locus? Yes or no? An emphatic no, right? I feel like I'm directing an orchestra, and I won't be doing that on the final. You're on your own on the final. But here you have no. You had already told me with your looks, you gave me the look this time, that the root locus was there. That's the only potential closed loop pole locations for proportional control. And what you do is live on that line. And you know how big K can be before you go unstable. If you crank up the gain to get beyond that point, you've gone unstable. What's the steady state error going to be for this proportionally controlled system? Will it be 0? Will you have zero steady state error due to a constant input in your closed loop system? You could derive it if you didn't see it, but you will not have zero steady state error due to a constant input. You'll have some error between where you want it to go and where it actually is, and that will depend on where you actually place that closed loop pole. But if you commanded your system to go to 2, it's not going to go to 2. It's going to maybe go to 1.7 or maybe 3/4. You're going to have a constant error in a proportionally controlled system where your pole is starting at something other than z equal to 1. So now somebody says, I'm not happy with that. I want zero steady state error. What kind of controller would you use then? Now you want a PI controller. You want to put an integrator into this controller. You force an integrator into the controller, and now, if we have a PI controller, what's that look like in terms of a transfer function? I'll do the hard part. A K. There's a PI controller. We're forcing a pole at 1, so I can immediately come over here and go, there we go. And to make my job easier, I might actually put my 0, my alpha, I might put it right there. And then what happens to my root locus sketch? How many pieces of the real line, how many segments of the real line exist? I have 3, don't I? But one of those 3 is kind of not really even there because I've canceled my pole at 3/4. Is that allowed? I made such a stink about not canceling poles and zeros. But where is it okay to cancel? Inside the unit circle. If you're getting close to the unit circle, you still may not want to cancel. But ideally, theoretically, in this class, as long as you're inside the unit circle, we'll allow you to cancel poles and zeros. Never, ever, ever cancel poles and zeros outside the unit circle. The root locus now has the exact same structure as it had before, except now you have that piece. And now you're guaranteed of having 0 error due to a constant input because you've located a pole at z equal to 1. So now how do you pick the k? Now I've said that, oh, my c of z is k, z minus 3/4 over z minus 1. K is selected for. How do I select K? What decision might I be thinking about in order to select K? DC gain. What is my DC gain now? If I calculated the DC gain of my controlled system, which would be, let's say I'm now calculating the DC gain of C of Z, G of Z, my loop gain, what's the DC gain of that? I could plug in my values and the factor of Z minus 3/4 goes away, and I have K over Z minus 1. What's the DC gain of that? What's the DC gain of that? K over 0. What's happening? It's blowing up, isn't it? Which is fine. You want a big gain at DC in your loop gain. That's what's driving your steady state accuracy to be so good. You have a really big gain at DC in your loop gain. That's a good thing. But that's not why we're picking K. K doesn't influence that at all, does it? We could have K anything we wanted, and we would still have well, as long as K is something other than 0, and we would have infinite gain. We would be guaranteed of having 0 steady state error. So how do we pick K? Pardon? We would definitely want to make sure that we picked K such that the closed loop pole, which I might represent by a triangle, is living inside the unit circle. We definitely wouldn't want to pick the gain big enough to push that triangle outside the unit circle. We want to preserve stability. Is there anything else we might want to do with K? Or use K to achieve? What have we focused on so far? Steady state accuracy and stability. Is there anything else that we can talk about? Settling time, a performance spec, right? Do we worry about percent overshoot? That's a performance spec. What else do we have? Peak time, that's a performance spec. So we didn't talk about performance specs, but in this particular case, because of the way I located my 0 right on top of that pole, I still have effectively what kind of a system? A first order system. And where is that closed loop pole always going to be? It's always on the real line, and you want it to be inside the unit circle. But if you have a real pole, hopefully it's between 0 and something, 0 and 1. You probably don't want to push it beyond 0 because then it's negative, and every other sample you're going to be changing sign. And you may get tired of banging back and forth, changing the sign. But what happens with that triangle? Now that triangle can influence settling time, can't it? Performance or speed of response. So K can be selected for speed of response. If you wanted your response to be deadbeat, I know you wanted me to say that word. If you wanted your response to be deadbeat, where would you locate that triangle? At the origin, at z equals 0. Do you see that you can now push that triangle around, and once you've located that triangle, you can solve for the K? You say, oh, I'm going to be the designer. I'm going to design that triangle here. You place it, then you solve for K, and now you're done. You now know what your closed loop poles are going to be doing. Suppose that somebody says, oh, but I didn't really very accurately model my system. Maybe it really wasn't, 1 over z minus 0.75. And I've been forced with my controller. I designed a controller to have a 0 at 0.75. Now what happens? Let's look at what happens and this we could say, what about uncertainty in the actual pole location? Maybe the system didn't behave. Maybe you modeled the system in air and the true system is a little different than your model. We modeled it as 1 over z minus 0.75. But what happens now if the true system has a pole somewhere other than 0.75? Well, you can now pull out your handy-dandy z-plane and examine that. What if you're still using a PI controller, so you now have a pole there and a 0 at 0.75. That's your controller. You've designed that based on what somebody gave you as the model. But let's say that the actual true pole of the system was at 0.7. So here, let's say the true pole of the system is at z equal to 0.7. What's the behavior now? Can you tell somebody what's going to happen to the system behavior now in the true system? How do you tell them, how do you analyze this system's behavior, this closed loop system? You still have just the gain that you've introduced in your controller based on where you'd placed your triangle before. But what's going to happen now? What are the potential closed loop pole locations? If I say potential closed loop poles, what are you thinking? Root locus, RL. Potential closed loop poles, you're thinking RL, aren't you? Root locus. Yes. Pardon? So what's the true pole of the system at z equal 0.7? Let's say that you had a circuit. Let's go into the analog case. Let's say that you had a circuit and you were told that the model had this resistor and this capacitor value. And in fact, the capacitor was not what you were told. And so your RC product was not quite what you were told it was going to be. Here, you were told the pole was at 0.75. Oh, the true system really wasn't. It had a pole at 0.7. Now you're saying, well, I'm fixed with the controller that I designed based on what you gave me, but what's going to happen in the true closed loop controlled system? You can tell us by sketching the root locus. Where are the potential closed loop poles?
So when you were designing it, you under the assumption that the 0 was at 0.75. Like, isn't that pretty important because it cancels out the 0 and like leaves there to the point where the transfer function turns to 0, like the system that might cause a lot of problems.
So now we're trying, so the question was, are we going to end up with problems because of us basing our controller on a plant that had a pole at 0.75? And we're trying to answer that question. Is it going to give us problems? That's what we're trying to answer. We assumed our pole was at 0.75, and so we based our controller, so we fixed a 0 at 0.75. And we said a PI controller, that's giving us a pole at 1. Now we have our true plant's pole at 0.7. What's the root locus of this look like? How many pieces of bread do we have? 4, don't we? How many of those 4 pieces of bread, people are listening to this and going, I thought you were in electrical and computer engineering. It sounds like a baking class to me. Well, we just do everything in electrical and computer engineering. We can even bake bread. So now we have this bread. Where is our root? Where are the branches of the root locus? How many branches do we have? 2. We had 1 before, didn't we? Because we exactly canceled that pole. Now we have 2. So there's a little change. But you would hopefully say that is part of the root locus, and the other one is right here. And we've picked a gain value, and what's going to happen? Well, now, for that gain, will probably be about where we picked it before, there, but this one will be close to that 0. And that 0 is sort of canceling that closed loop pole that's approaching it for that choice of gain k. So what's the net effect? Well, you have this closed loop pole very close to the 0, which kind of goes away. It doesn't completely. And you have a pole about where you set the previous pole for this particular choice of true system pole. Somebody goes, well, that's maybe not where it was. Maybe it went the other way. Maybe it was at really 0.8. What happens then if the true pole was at 0.8? This is what we put down because of our original model that we were given. There's our 0 and pole due to the PI controller. And now somebody says, oh, our true system pole is at 0.8. Now what happens? Can you sketch that root locus? That's 2 poles and a 0, isn't it? So now you know that you have these 2 coming together, going over, and one going there and the other one here. And what's going to happen? Well, for the choice of gain that you've picked, you'll probably be there and you'll be right there. And how does this behave? Very similar to the other case. We have a closed loop pole that's almost getting canceled by the 0, and we have our dominant, the pole that we wanted, pretty much in the same place that we had it when we had that model being a pole at 0.75. That's how you could now start to analyze or examine the behavior due to uncertainties in your system. And this root locus analysis is sort of saying, you know, it's a pretty robust way of designing controllers. Our system response, our closed loop system response didn't change that much, even when our system changed a little bit. And we didn't have to necessarily exactly cancel the pole with the 0. And we still had pretty good behavior. That's the takeaway from that. Yes?
So, does the system necessarily go slower or necessarily will have
So now the question was, wouldn't our system response be necessarily slower? You will have a mode at that triangle. Both triangles will give you modes, won't they? But now one of those modes is almost canceled by the 0. So you're not seeing that, although it will influence you, and it may be a very slow tail, but the majority of the system will be determined by that sort of isolated triangle giving you the closed loop behavior. So yes, you will have a tail, but you won't see that tail very much because it's almost being canceled by that zero of your controller. But you do have two closed loop poles now, and you had one before. Yes?
I just had a question about like the closed loop transfer function formula with the after the CDX numerator. Like if the zero doesn't cancel, would that like cause the closed loop transfer function to be zero at certain points that it?
So now what you can do, the question was, will that change in your system really do more than what I illustrated? And my response would be, go home and see, and it really is not going to change too much more than what we've talked about with the root locus. Because your G is still 1 over Z minus, instead of 0.75, it's at Z minus 0.7. And that actually cancels in the numerator and denominator of both. Let's now look at another example. Suppose we had this plant and somebody says, let's control it with a PI controller. What's C of Z structurally? What's the controller structure? I'm going to use beta for the second example, and now we have Z minus 1. Can you already anticipate what the root locus looks like for this PI controlled plant, G of Z, 1 over Z minus 2? Is that our friend 2 poles and a 0? Depends on beta, but where's beta located? Your poles are fixed, aren't they? Your plant has a pole at 2, and your PI controller has a pole at 1. So we can immediately put those down. Now, where are you going to put your beta? Are you going to locate your beta between 1 and 2? Is that a good idea, to put beta between 1 and 2? What would that force? If you put your 0 between 1 and 2, do you see that that branch of your root locus is always outside the unit circle? You're stuck. That's not a good place to put your 0, is it? So now I'm going to try to erase that. Good luck. So we'll see. I could press the undo, but that's too easy. I knew I wanted to do that. So here we go, and that's supposed to be a straight line. Oh boy, that looks even. So can't press the undo, that's too easy. All right, so I have that. Where's my beta? You know it's going to be not between 1 and 2, not beyond 2, right? Because then that pole would always be going to the right, unstable. You need it here. And then you know what it looks like, don't you? You now know that your root locus, you'll have to crank up the gain enough to get your poles, your 2 branches, simultaneously inside the unit circle. But now here's a different philosophy. Instead of picking beta and then sort of anticipating where your branches are, which you kind of know quite a bit because of this 2 poles and a 0 structure, But what if somebody said, can I pick closed loop pole locations, can I pick triangles, and then figure out if beta can be adjusted to make my root locus go through those triangles? Do you understand that thought process or that thinking? Now locate your triangles and see if a beta exists to make that happen. That's the process. Let's select beta, the 0 location, to produce a desired root locus path. But in fact, we're going to do it sort of the opposite. We're going to pick the triangle and then locate beta from that. So K is used, but once we have beta, then we can find K to put us on those triangles. So K is used to fix the dominant closed loop poles. For whatever reason, let's just suppose, for performance specification purposes, suppose one wants Z delta to be at 0.9 plus and minus J 0.1. If I gave you that on the final exam, could you tell me, if this is a two-pole system, what the performance specs are? If I give you Z delta and these are the closed loop poles, you should be able to tell me the settling time, peak time, and percent overshoot. So now what we want to do, suppose somebody says, I want my closed loop poles at 0.9 plus and minus J 0.1. Now the question is it possible to have closed loop poles at Z delta with a PI controller? If we have a PI controller and our plant was giving us a pole at 2, a PI controller immediately puts a pole at 1. And now what somebody is saying is they want the triangles to be right there, 0.9 plus and minus J 0.1. Maybe I shouldn't do that in red. How are we going to make this happen? Can we make this happen? We're asking, is it possible to use a PI controller and achieve these triangles? So we want our red lines of the root locus to pass through those triangles, don't we? That's what we're saying. And what we're saying is it possible to locate a beta such that we have a root locus, 2 branches going through those triangles? How can we make that happen? What tools do we possess that will allow us to make that happen? What do we know has to happen at that point if it's on the root locus? If that triangle is on the root locus, if we're pinning the root locus at that point, what do we know has to be true at that point? The phase angle has to be minus 180, doesn't it? And we know the phase at that triangle from the pole at 2 and the pole at 1. We could quickly get on our protractor and measure those angles. We only have one more angle to deal with, and that's the angle due to the 0 beta. So can we slide that around such that the algebraic sum of that zeros angle with these other 2 pole angles equals minus 180? That's what we're asking. So let's now use the phase angle condition to find beta, where beta is the location of our zero. And we could just draw something in here and say that's beta. And we don't yet know where that is. But that tells us then that we have this angle, theta sub z. We have this angle, theta p1. And we have this angle, theta p sub 2. We have three angles, and we're interested in their algebraic sum. The phase angle condition now says that theta z minus theta p1 plus theta p2 must be minus 180 degrees. What's theta p1? That one we can actually determine by inspection, right? We go up 0.1 and over 0.1. We know the acute angle is 45. We'll just take that away from 180. So theta p1 is 135 degrees. We know this angle. What's theta sub p sub 2? I like to just play with the acute angle because my calculator maybe only does inverse tangent for plus and minus 90 degrees. I know I'm vertical how much to calculate this acute angle associated with theta p sub 2. What's my vertical rise? 0.1, isn't it? I'm glad you said it because for some reason I was pulling a 1/2 out of the air. I don't know where that was at. I think all of these previous before this lecture I was dealing with a lot of things that were plus and minus j1/2. So look at lecture 7.1 A and B, commercial time, huh? Anyway, where were we? Vertical height here of 0.1. What's the adjacent side? 1 and a little more, right? 1 plus 0.1 or 1.1 is the horizontal distance. Is it clear where that came from? This is not a very big angle. It's 5.194 degrees, so that theta p sub 2 is 174.8. We now know that we have theta sub z minus 135 degrees plus, let's say, 180 minus 5.194. The reason I did that is because I have a minus 180 degrees over here, and that minus 180 cancels that minus 180. And now I just have to look at this small difference between 135 and minus 5.1. Or I have theta sub z is 135 minus, or it's 129.8 degrees. Is this going to be okay? Let me try to expand this picture. Suppose this is my triangle. There's my vertical height. And where is beta? If my angle theta sub z is 130 degrees, where is beta? Is it to the left or to the right of that triangle? It's to the right of the triangle, isn't it? Because 130 degrees is more than 90. So that beta has to be over here. And this point right here is 0.9. And I can now maybe solve for this distance, which is x bar, where beta now is going to be 0.9 plus x bar. And x bar I can compute because I know this angle. And x bar, this is why you need your trigonometry, isn't it? You can now find that acute angle and use that with this tangent information and find the adjacent side x bar. X bar ends up being, since I'm out of time, 0.08333. And then what do? Now you know your zero location. You adjust the gain k. You use the magnitude condition to put your closed loop poles right at the triangle. And we'll pick up at that point next time or somewhere close.